Hello. I believe we are now live. Hello. And I need to reorient myself. Hello. How's everybody doing? I just realized that I'm wearing a Christmas sweater, even though it's the middle of November. So please don't judge me for that. But it is one of the warmest sweaters that I own, and it is cold here in Canada. So please do forgive me for that. All right. So a couple of things before we get started. I am very excited that we are resurrecting this meetup. It's been many months since we've done one of these, and I think it's going to become a regular thing. We won't be doing one in December because holidays and whatnot, but starting in January, we will be doing these regularly, and we will be bringing on as many interesting guests for interviews, presenters for demos and presentations as we can. And if anybody is interested in being a presenter or giving some kind of interview or demo, please do reach out to us. You can send an email to team@suborbital.dev if you'd like to get in touch with us, or you can send a message over Twitter or Discord or any of the places where we exist. So I am Connor. I am the founder of Suborbital. We are going to be hosting these meetups, but this is not a Suborbital show. This is a WebAssembly show. We are welcoming anybody and everybody to be guest presenters, and we hope that a wide variety of people will come and join us to share what they're working on, and hang out and have a good time. So this is a meetup, not just a stream. So there is a place for us to hang out. If you look at the ticker across the bottom of the screen, you'll see that there is a Discord link server. And I'm going to post that same link in the YouTube chat. And that will get you into the WebAssembly Discord server. And within the WebAssembly Discord server, there is a wasm-NA channel. Now, it is a voice channel. So when you join it, it's going to turn on your mic and everything. Just mute yourself and turn off the sound, and that's okay. But when you hover over the channel, there is a little chat bubble. Click on that. That's where our real-time chat is going to happen. Now, of course, you can also make comments in the YouTube chat if you like, and we will see those, and you can ask questions to Alex and Ramon with either of those two chats. We will keep an eye on both. And then after the interview is over and the stream ends, then we can all turn on our microphones and or cameras in the Discord chat and hang out and just talk if we like. So with that being said, I'm going to bring up Ramon from Suborbital and Alex, who is a key maintainer of the WebAssembly and Rust ecosystem. And I'm going to let them take it away for the main show of this evening. So how about it, guys?
Thank you so much, Connor. And thank you, Alex, for being here. And thank you, everyone, for tuning in. I'm super excited to be doing this. It's my first time attending a Wasm North America meetup, so it's a joy. I'm kind of cheating because I'm not tuning in from North America. Hello from Vienna in Austria. I am not going to tell you what time of the morning it is, but it is rather late. And hello, Alex. How are you doing today?
Doing fantastic. It's nice and warm. Well, actually, it's kind of cold out here in the Midwest, but it's not too bad.
Good to hear. Yeah, it's getting pretty chilly here in Vienna as well. Well, thank you so much for tuning in, folks. If you're wondering what's going on today, you might have seen on the banner and on the meetup page, we're going to be talking about how Alex, sort of going into the story of how you added WebAssembly support to Rust, what that took, what it looked like at the time, and how it looks now and moving forward into the future. But before we hop into that, Alex, I'd love to give you an opportunity to tell us, a little bit about yourself and what it is that you do.
Yeah, definitely. So, hi, my name is Alex. I live in the Midwest, and so I'm an engineer who works at Fastly, and I work on the WebAssembly runtime aspect of Fastly's Compute Edge product, where whenever an HTTP request comes into our CDN, we run some WebAssembly code for it. So I work on Wasmtime primarily, which is an open source project run by the Bytecode Alliance, and it is specialized. It's an out-of-browser runtime for WebAssembly, so I get to have all the fun of implementing all this as well in the same manner of JS engines having done all that themselves.
Sorry, Alex. I think your microphone might have done a little thing there. I don't know if it got caught off there. Could you try speaking again, please?
Yeah. Do you hear me now? Is anything sounding
perfectly? I don't know what you did, but keep doing it.
All right. Well, apparently I have ghosts in my computer at some point I got to figure out. But anyway, so I have historically worked a very large amount on the Rust programming language and the standard library in various ecosystems around that. As Ramón was saying, I did a lot of work to bring WebAssembly into Rust and get WebAssembly as a really nice target to use in Rust. And so I don't do quite as much of that nowadays as I'm focusing a lot more on Wasmtime, but that's sort of what I do nowadays.
Fabulous. Thank you. Well, folks, we're about to jump into our fireside chat, and I'm going to be asking some questions to Alex. But here's the thing. This is a meetup. I want to ask you all to please drop your questions into the chat, as Connor said, or into the YouTube chat, and I'll be bookmarking them, and we'll be having a little Q&A session afterwards, being conscious, of course, of Alex's time, who's very kindly lending it to us. And yeah, let's hop right in. So you and I looked this up. So in 2017 and in 2019, respectively, you added two compilation targets to Rust. One of them is wasm32-unknown-unknown, and the other one is wasm32-unknown-wazi, as it was known at the time. So from what I understand, this is adding wasm wide support to Rust. And folks, in case you're interested, I took the time preparing for this to go and read those pull requests. And let me tell you, you'll learn a lot. This was my first time reading pull requests from and in projects that I have never contributed to before. I haven't contributed to Rust myself. So it's kind of like a really interesting journey. And I want to start with the names, if I may, because if you look at a name like wasm32-unknown-unknown, it's an interestingly odd name, if I may say, especially if you're not familiar with writing targets. Now, I did later find out that this is called a target triple, and I was wondering if you could please maybe give us a little bit of a background on what these mean and why they're named like this.
Yeah, definitely. It's not to be intentionally mysterious, despite the actual name. But the irony is that despite being called target triples, they often come in quartets or also in doublets or only in pairs. So this is where you can break apart the wasm32 unknown into three pieces: wasm32 and then unknown. But other targets like Linux will actually have x86-64 unknown Linux GNU, which is whole four different pieces. But the idea is that originally was target triples, and then we added pieces on later to get the four pieces. And then we also figured out how to shorten it down to two, which we'll talk more about later, I suspect. But of the three pieces of wasm32 unknown, we've got wasm32, which is the target architecture. So you see ARM, wasm32, x86-64. The second piece is what's called the vendor, which is unknown. And most Rust targets have unknown. So Windows things have PC. I honestly don't really know exactly what we use the vendor for. It's just kind of there because everyone else seems to use it. And then the third one is the OS. So you'll see that the Linux on Linux. So you see Windows and Windows. And I think you see Darwin for Mac OS. And so those are the three pieces of wasm32 unknown. And so the reason we ended up calling it that was that the goal here with the initial introduction of the target was to be a very bare bones aspect of WebAssembly. So it's not assuming any vendor, not assuming any, not really vendors for WebAssembly per se, but not assuming any OS. So that primarily means it's not going to import anything. So when you use the standard library, No functions are imported into your WASM module, so you can't open a file, you can't make a TCP connection. You yourself can go import things, but the standard library won't do any of that for you. So that's sort of like the general idea of the target behind it at the time.
Yeah, thank you for clarifying that. It's really interesting to think that, yeah, I mean, Wasm doesn't have a vendor and doesn't have an OS, at least at this time. But the 32 I found interesting because I never really thought about what that architecture would look like for WebAssembly. So you mentioned that there might be a possibility of also 64-bit or not an ARM one, because that's a computer architecture. Is that correct? Like a CPU architecture.
Yes.
Yeah.
But yes, for 64-bit, this is where the WebAssembly standard gives WebAssembly the concept of what's a linear memory, and all linear memory operations by default use a 32-bit address. And so while it's technically just WASM, we ended up calling it WASM32 in the implementation side in LLVM and also in Rust. And that was sort of to emphasize that the pointers are all 32 bits large. But there is an experimental, or I suppose, proposal for WebAssembly called Memory 64, which is going to extend WebAssembly so it can not only have 32-bit memories, but it can also have 64-bit memories. So that's going to be such a major difference in compilation targets for Rust. That's why we kind of reserve space to have this future target. Eventually, we'll have WASM64, and it's actually experimentally in the compiler, but it's not really fully ready just yet because the actual WebAssembly proposal itself is still kind of in its extends process. I'm working through that.
Cool. Thank you. So now, if I understood correctly, just looking at some of the code, this is not the first WebAssembly target for Rust, if I'm not mistaken. The first one was an Crichton one. Is that correct?
That's right. That's where all of WebAssembly is predated by Crichton. Crichton was sort of the birth of wasm-bindgen, which is where you compile a bunch of C and C++ code to JavaScript, but it's like very carefully crafted JavaScript, so it runs just right in browsers, so it's super fast. And then Wasm was sort of the evolution of that, where let's kind of make wasm-bindgen like more widespread things. That was where WebAssembly originally came from. So this is where originally we had wasm-bindgen unknown Crichton. So that was where the target was considered JavaScript, the vendor was still unknown. The platform, or the OS at the time, was considered Crichton, sort of like the toolchain around that. And so prior to the unknown target, there was an upgrade for WASM32 unknown Crichton. So yes, that all existed in the compiler at the time, just used very different backend things internally. So this is where it used the internal scripted backend for actually compiling everything, as opposed to the unknown target, which was using the LVM backend, which I assume I can definitely. I don't want to get too far ahead of myself.
Thank you. No, that's super helpful. So like, okay, so originally we were using Crichton, and as you correctly said, when creating this WASM32 unknown target, you mentioned in the PR very purposefully that you did not want, that you wanted to forego Crichton in favor of using LLVM. And I mean, you've told us a little bit about Crichton, but I'm wondering what was the reasoning for deciding to forego Crichton?
Yeah, definitely. And there's a lot of history here. And I might have to pause for a moment because this is like 5 years old at this point. So it takes me a little bit to dig all this up. But so Crichton was historically built upon an LLVM backend called FastComp. This was a fork of LLVM at a very old point in time. I don't actually know the original history of this. And FastComp was tasked with taking LLVM IR as input and then generating JavaScript code as output. But this was a fork of WebAssembly, and this never actually made its way back upstream. So it was sort of always diverged from WebAssembly. It was based on like older versions of LLVM, and it was just a whole different compilation model. Like the whole model, like it wasn't centered around like modern kind of what you would expect from native toolchains. So there weren't exactly object files in the same way that there are native toolchains. The linker was a little different. But anyway, just to say there was a lot of history around that. That was how Crichton was working. But that was not really where the WebAssembly target was going. So this is where official WebAssembly support was added to LLVM upstream, sort of in this time period. So after FastComp, before we added the WASM32 unknown target. So at the time, Crichton had not migrated to use the WASM backend in LLVM, but that was sort of it was considered the future. Like even Crichton at the time, it was like they wanted to do it. It was going to take some work to actually get that done. So the goal that I had at the time was to sort of get on that train as soon as possible, get us working on the LLVM WebAssembly backend, start getting bug fixes there, bug reports, user experience, all that good stuff, kind of flushing all that out. And there's a lot of various trade-offs, but I think most of them were in favor of the LLVM backend. So, for example, this has official object files. It's got a much faster linker story going on there. It's more integrated with the LLVM toolchain, and it's all upstream, which is sort of the best part of, we just sort of naturally pull in LLVM updates, and we don't have to worry about kind of keeping fast comp and Rust LLVM and upstream LLVM all on sync at the same time.
It's fascinating. Thank you. Just a couple of notes for folks watching live. If you've got any questions you want to ask Alex, please feel free to drop them either in the YouTube chat or in the Discord chat. I do have a little note here from backstage. Alex, is it possible if you check your settings to make sure that StreamYard is using your headset microphone? Because it kind of sounds like it might be using your built-in one. Sorry to...
A lot better, doesn't it?
Oh, that's much better.
Sorry, it was using the wrong microphone. That is my bad. I apologize for that.
No worries, no worries. Thank you, Connor, for catching that. Okay, right. So you decided to forego Crichton in favor of LLVM and some of that other tooling. I was wondering how difficult was that? Did you encounter any obstacles doing so?
Oh yes, very much so. The LLVM backend for WebAssembly was very new at the time, and so it was sort of in development for Crichton. A lot of Crichton developers were working on it at the time, but it was not done. It was not fully integrated. It had not had all the bugs fleshed out. So we had a whole slew of linking issues. We had compiler bugs. We had miscompilations. We had LLVM panics. Kind of the whole gamut of whenever you write a new compiler backend, what can go wrong? Everything went wrong. So it was a lot of fun kind of debugging all that and kind of narrowing things down, sending bug reports upstream, getting all that fixed and everything.
Yeah. Right. And I imagine that made things a little bit slower to get up to speed than preferred.
Very much so.
Cool. And when doing so, like another thing that you noted that I found quite interesting is that a lot of components that are usually built into these either compilers or runtimes, you ported to Rust. Please correct me if I'm misunderstanding, such as dlmalloc and binary-n. And dlmalloc is from my understanding, from my limited exposure to like the world of Objective-C programming from back in my macOS programming days, comes from memory management, allocating and deallocating memory. But I was wondering, could you tell us about these? I'm curious also about binary-n and what was the reasoning behind porting these?
Yeah, definitely. So this is where WebAssembly is a very low-level target. So it kind of only gives you math. You can add numbers, you can multiply numbers, you can move things from memory, but that's kind of it. It doesn't really give you any high-level operations there. And additionally, this unknown target was supposed to not import anything, which meant it couldn't assume the host gave it anything or had any imports as a result of that. So what this all amounts to is that it's extremely common in Rust programs or pretty much any program in the world that you want to allocate memory. It's a relatively low-level operation that a lot of kind of like a GC language like JavaScript or Python doesn't really give you low-level access to this, and Rust sort of abstracts it away where you don't have to worry about it too much. But under the hood, very common to say, I want 10 bytes of memory, and then sometime later you say, I'm done with these 10 bytes of memory. Please let someone else have these 10 bytes of memory. So that's typically what's called a memory allocator. So WebAssembly doesn't have a memory allocator. It gives you the ability to say, give me 65 kilobytes of memory, but that's massive. And it's also more permanent, has kind of resource usage. It's more like I would like just give my process more memory kind of style thing. So anyway, dlmalloc was a kind of generic memory allocation implementation written in C originally. And it was just sort of a good example of, it was a trade-off between code size, so it's not too big, it's not too small, speed, so it's not too fast, but it's not too slow either, and portability, where dlmalloc had been ported to, I think, dozens and dozens of Unix platforms at the time, and was basically a perfect target for WebAssembly. So Rust needed a memory allocator. We needed to do something, and there wasn't exactly any off-the-shelf that were kind of suitable for the standard libraries use case. So I chose dlmalloc and I just ported it all to Rust, which I just kind of stared at the C code, wrote some Rust code and just kind of went one-to-one and everything. And so that was how dmalloc was born, and that was basically just a translation from the C code to the Rust code. And that means that in the standard library, we now have a memory allocator, and that means that when you compile to WebAssembly, you don't have to pull in anything else. It's all baked in inside there. Makes sense for dmalloc. I can cover binarian next.
Yeah, please.
Sure. So binarian was actually not ported to Rust. This was it might have been a little confusing from the PR, but it was more of a toolchain side of things. So this is where talk about history and things going on here. So binarian is a project that was spearheaded by the unscripted developers, and it was sort of the efforts at the time to get there to kind of get all the WasmJS and like unscripted output over to WebAssembly. So binarian is kind of like a nice toolkit for doing lots of different stuff with WebAssembly. Like nowadays, one of its flagship features is a command line executable called wasm-opt, which it'll take WebAssembly module and give you WebAssembly module. But the idea is it optimizes in between there. So it has its own inlining, has its own WebAssembly specific optimizations, all that good stuff. So at the time, binarian was actually the only way to get output from LLVM and then produce a WebAssembly executable. So I was talking about how there's a lot of bugs early on in WebAssembly backend. So nowadays you have a linker to officially do this. You get object files, and you can link it all together, but none of that existed at the time that I added this target. So I was very antsy at the time. I wanted to get this landed, so I wanted to get anything working whatsoever. And so this was where I took the one thing that worked, which was Emscripten at the time, and I think what it did was it was actually parsing like the textual assembly output of LLVM, which is sort of a misnomer because it's not really it's not the text format for WebAssembly. It's sort of an LLVM specific thing. But anyway, parsed all that and actually generated a WebAssembly module. So this was a piece of compiler tooling, which we took the C++ code, or binarians all written in C++, so we compiled all that, linked it into the Rust compiler, very similar to what we do with LLVM. We just compile all of it and link it all straight in. And then we took all that, and that was what actually produced the WebAssembly executables at the time. Now, all of that has since been removed since it was just a temporary stopgap until all the features of LLVM came into place, but that was sort of basically just a temporary transitional period.
Yeah, that's like I think it was in the WASI PR, and I could be wrong about this, and I'm getting a little bit of ahead, where you mentioned that the additions to LLVM have made this significantly easier, such as the addition of LLD.
Right.
And I'm wondering, could you tell us a little bit about that and maybe what it stands for?
Definitely. Well, I can tell you about it. I actually have no idea what it stands for. The naming, I believe, so all LLVM related things, they all got to be called LL something. So you got LLDB for debugging, you got LLVM for
Right.
the whole. LLVM technically stands for low-level virtual machine, but it's not actually a virtual machine. It's more of a compiler toolkit, so we can ignore that. But anyway, LD is the system linker on Unix. So it's kind of what you typically use to take object files and generate an executable file you can actually run. So I believe LLD is the LLVM's version of LD. So they just put another L on front. But anyway, so the idea is that LLD is a linker written in C++ for the LLVM toolchain. It's got a whole bunch of targets, so it can generate ELF, which is kind of Linux stuff. It can generate Mach-O, which is Mac OS stuff, and it can generate Cough, which is Windows stuff. But then other extra support was added for WebAssembly, where a object file format was defined for WebAssembly. So it turns out they're actually just WASM files themselves, and then WASM-LD, or actually I should say, so LLD, which has a driver called wasm-LD, it's the same program, just called a slightly different thing, is used to link all of these object files into one final WebAssembly binary. So this performs what you would typically expect of a linker, which is it takes a look at a bunch of compiled artifacts really quickly, in theory, creates one final artifact with everything shoved in there. So this is what powers the separate compilation model of Rust, of like when you download Rust, you get the standard library, but it's a pre-compiled version of the standard library. Then you write your code, you compile that code separately from the standard library, and then LLD is the thing that comes together, slurps it all up, and generates one final WASM binary to run.
Cool. And fun fact, Alex, because you and I talked about this previously, I did find out where the name I didn't find out. The team at Suborbital and I went on we were wondering about this, and one of us found out that LD is actually short for load or loader.
Oh, wow! I think that is some ancient naming there some really ancient roots, because it's not really loading a whole lot nowadays, but I suspect it was way back when.
It's it's definitely been around for a while. That's really cool. Thank you for expanding on that. And taking all of this, all of the, using LLVM as this sort of intermediary linking mechanism. I'm wondering, did this run you into any obstacles? Did it collide with Rust C? Could you tell us a little bit about that?
Yeah, this actually, it kind of just greatly simplified everything, and everything got way nicer after this. And the reason for that is prior to WasmLD, the way that you would generate either AsmJS or stuff for Mscripton, or even just the Wasm target at the time, the unknown target, would be every compilation was sort of an LTO style compilation. Now, LTO stands for link time optimization, but what it sort of meant was that the compiler is slurping up all code everywhere and then optimizing it. Now, that's a really slow operation because LLVM is not built to have your entire program in memory all at once and then rip through that. I mean, it works just fine, but it is very slow. So this meant that even the most trivial programs on WebAssembly took forever to compile because you had to slurp up all the compiled code of the standard library, re-optimize all of it with your code, and then have it all come out the other end. So WasmLD was the massive simplification, which is the more native style linking, which is it doesn't have to. It does look at the object files, but it's more of you can sort of think of it as like a glorified mem copy where it's just copying memory. So it doesn't have to like deserialize data structures. It's not re-optimizing or anything like that. So that was the main benefit of WasmLD, was it greatly simplified the compilation story. It made it much more reasonable for small programs, things like that. And honestly, the integration into Rust actually, the most fun part there was that the WebAssembly target was one of the first targets to use LLD, which meant that the default linker for WASM, or kind of the only linker for WASM, was WasmLD. It's not actually installed on anyone's systems by default. So to get it working in Rust, what I decided to do was to ship LLD with the Rust compiler. Now, you could kind of link it in, but it's really not built for that. So what we ended up doing was shipping another executable. So when you install the Rust compiler nowadays, you actually install the Rust C, the executable, but you also install an LLD executable. I think the name kind of varies from distribution to distribution, but the idea is that you're actually getting these two things bundled together, and that way when we want to link it together, Rust C will kind of do all your compilations, and then when it would invoke the linker, it invokes its own personal WASM LD binary that it's got kind of shoved in its sysroot somewhere. So that was a fun time sort of figuring out the distribution for all that, because this was one of the first targets. And it's been really nice to see it grow since then, where LLD is not just useful for WebAssembly, but it's also very nice for other targets. It's often so most Linux systems come with something called bin utils, which is from like the GNU LD style stuff. But that linker is very, very old and has very reliable, but not always the fastest thing in the world. And so LLD can also be a very large speed up for native targets in addition to WebAssembly. And so people have been experimenting with that, trying to get LD used in more context, not just WebAssembly. It's been kind of fun to see that grow.
That's awesome. Thank you. And it's really interesting to see, how these considerations start out. Like one thing that I found really reassuring for myself as a developer was seeing that a lot of these things start out as experiments, as hacks, just
Yes.
Let's get it to work and then figure out how to make it better. Cause it's kind of like what we're taught when we're getting into coding, the sort of like notion of divide and conquer, fix the big problem and then optimize the smaller parts, which is really cool. So when you wrote this PR, you mentioned, of course, that at the time of writing, it wasn't production ready, this target, but I'd love to give folks an opportunity to hear from you how that's changed since then, and how it's being used now.
Definitely. So 5 years has passed since that first came in, and so thankfully it is definitely production ready now at this point. A lot of bugs have been fixed in the WebAssembly backend, not only for LVM, but in Rust C, various integration issues. Everything is basically has been ready for a very, very long time now at this point. So can definitely say, if you're no need to hesitate for using WebAssembly in Rust C anymore. But some of the flagship use cases we've seen, so a lot of WebAssembly is originally obviously growing on the web, hence the name WebAssembly. And so in the early days, another project that I was working on at the same time, like getting all this integrated, was called wasm-bindgen. So wasm-bindgen is sort of one of the one of the main tools that you can use nowadays for taking your Rust code and running it on the web. And wasm-bindgen's job is to basically say that. So when you're working with WebAssembly, WebAssembly only gives you integers. So you get i32, i64, f32, and f64. And those are not helpful because what about string? What about records? What about structs? What about lists? Like all this fancy stuff. And so what wasm-bindgen is doing is it's helping you bridge that gap. So wasm-bindgen generates JavaScript glue code for your WebAssembly module, and then you can interact with JavaScript with strings, with Rust with strings. So you don't have to really worry about all the details of how these things are actually passing in between there. There's a lot of history to wasm-bindgen, but that's sort of one of the main use cases for Rust and WebAssembly nowadays, which is if you want to take Rust code and put it on the web, that's a great way to do it. There's other aspects. So WebAssembly has definitely very much grown in the out of browser space nowadays as well. So not only can you run WebAssembly on the web, but you can run it on your local computer with the various runtimes available to you at this point. And this is also the employer I work for actually takes WebAssembly modules and runs them in the cloud as well. So kind of another, not in a browser, so like different aspects of that. So anyway, Rust is all great for that nowadays. That's primarily using the WASM-32 WASI target, which we haven't talked too much about, but is definitely also production ready as well. And so kind of like it's another idea of taking Rust code and running it in all these various places.
That's awesome. And I'm glad you bring it up because that's exactly where I was going next. Let's talk about WASM-32 unknown WASI. So if I got the naming convention right, WASM-32 is the target, unknown is the vendor, but WASI is the OS.
Right.
So for folks that might not be familiar with it, could you tell us a little bit about WASI?
Definitely. So the unknown target, as I was saying, can import nothing, which means that it's suitable to run in any WebAssembly environment. Oh dear, I think I have lost video. Can you still hear me though?
I hear you fine.
Okay. Anyway, all good. But the idea is that you can run it in any WebAssembly environment, but the standard library, for example, can't do anything. So if you call println, nothing happens. If you call eprintln, nothing happens. If you panic, the program halts execution, but nothing else happens. You have no idea why it panicked. Doesn't print anything out. So the idea here is that because WebAssembly inherently, as an instruction set, can't do anything, it's limited in its use cases. So like for the web, we had to have various aspects of let's hook in like a panic hook. So when you panic, it'll go to console log, but you have to manually set that up. So WASI is sort of one of the ideas we have to fix this. So WASI stands for WebAssembly System Interface. And the idea is it's a standardized set of functions that you can import to your WebAssembly module, and that has a very clear meaning, because due to the standards and everything, of not only what the embedder has to give you, but what you as a guest or a WebAssembly program can rely on. So this has a common functions like print or kind of write to a file descriptor. It's got read a directory, open a file, get some random numbers, kind of what you would expect from just a basic system of I'm just running on a computer. Now, there's a lot of design goals around WASI as well, but the idea was basically let's give it so we can empower the standard library to actually do these things. So when you use the WASI target, the binary that you generate will actually import some functions. So it's got some, in WebAssembly, you can import from a module and a function name. So all of those are listed for WASI. So to like import the write function or the randomness function or the exit function. And so that's required to actually instantiate that WebAssembly module, which means it's not quite as versatile because you actually have to have this in the runtime. But the goal with WASI is like WASI is in theory ubiquitous throughout WebAssembly runtimes. So anyway, that's the motivation behind WASI and sort of what's going on there. And that's basically I guess I should say it is primarily used nowadays for out of browser scenarios. So it was always envisioned that WASI would have a polyfill, which actually would allow running it on the web as well. That hasn't really quite come into play where you can do it, but it's not necessarily production ready, and it's like a very widely recommended thing to do. I do think that'll change eventually, but the idea WASI's also undergone a lot of changes in the meantime. But that's where like so if you run it on Fastly's infrastructure, or if you kind of run a WASI program locally, or kind of has a plugin style API, a lot of those use cases will use WASI. It's the standard way of I'd like to print some bytes because they can't necessarily assume JavaScript and the whole web platform as a result.
Awesome, thank you. And I suppose from when it comes to writing a WASI target in Rust, writing to a WASI target in Rust, there's some interoperability implied with Rust C, and I'm curious how, and C modules itself. How does that look?
Yeah, so this is where you often will want to integrate into your WASM module both C code and Rust code. So you want to have them totally linked together, very similar to sort of like a statically linked library or a dynamic library for a native target. And so the WASI was one of the first targets where everything, or I should say, actually, no, that's not true. Mscripton was the first target for doing this, where Mscripton was primarily developed for C and C++, and so Rust as a third language was where you can actually start linking everything together. The unknown target has some kind of funkiness where there's not really an official C toolchain for this. So there's not really a great way to generate C code that talks to unknown. So there's not really a great C interop story for the unknown target. But WASI does have a C toolchain. And so it's built on all the same technology that Rust is, where the WASI C toolchain is using LLVM, using the LLVM backend, using the same object file format, all that good stuff. And what this means is that it's really not that different from a native platforms where you just sort of declare these symbols are existing in C, or C does the same where it's like I declared this exists in Rust, and then by the time you get down to linker just says, oh, I will connect all those dots and generate a WebAssembly binary for you. So that's where it actually wasn't. It ended up being not really a whole lot of support inside of Rust C itself. It was mostly around just the kind of the general architecture of the tool chain of like we're all using the same tools. We all agree that a 32-bit integer looks like a 32-bit integer. More like Stark layout style stuff, but everyone agrees on all that, and that allows C and Rust code to intermix and interoperate within one WebAssembly binary, specifically for the WASI target at least.
Cool, thank you. And when you made this pull request, one thing that you proposed or that I found quite interesting was wasm-bindgen. And I was wondering, could you tell us about it and like how's it been adopted since then?
Yeah, definitely. So WASI as a system interface was sort of originally designed after Cloud API, which has a very strong POSIX roots. And so everywhere in POSIX you'll find file descriptors. Everything's an FD. Everything you can open a file, get a file descriptor, open a directory. You can open I don't know. You can get timers out of them now. You can get signals. You can get processes. I mean, everything's a file descriptor at some point. Well, I'm not going to go into the Plan 9 aspects of that just yet. But anyway, so the idea is WASI was very heavily rooted in POSIX as well, and so there was a very similar file descriptor for WASI. So this is what represents primarily files and directories in WASI, where you can open a file, get a file get a file descriptor or a WASI FD, but then also there's this notion of pre-opens where your program will just start with a couple of FDs available to it. The primary ones here are file descriptors 0, 1, and 2, which are standard out, or standard in, standard out, and standard error, just the standard like the standard IO streams. So WASI FD was it's just a 32-bit integer, but it's this 32-bit integer that you kind of pass to all these syscalls. So WASI is as specified, it's got a particular ABI. So when you call the write function, you got to pass it a couple of arguments. And one of the arguments is the WASI FD that you're writing to. And the other arguments are like what the buffers you want to write are and things like that. So WASI FD, it works relatively well today. It's probably going to be changed in the near-ish, well, in the future at some point. This is where WASI is going to undergo a lot of various changes for the component model, which I don't want to go that's way far ahead of myself, so I'm not going to too far into that. But so WASI FD has definitely worked out pretty well in the meantime, in the sense of it maps very cleanly to the Unix ownership model, kind of how everyone expects there. So a lot of code that expects just Unix stuff will work pretty well. And so that's one of the main reasons for it being used and being pretty successful this time.
Awesome. That's and I love that you mentioned. I know you don't want to go into it too much because it is quite far in the future, but like the WASM component model, I wanna link, if I may, real quick, a link from a talk from Luke Wagner, who spoke at Cloud Native WASM Day North America, who spoke about the component model. In case folks are curious, I'll drop a link there in the chat, where he talks about how this is kind of like the future of where WASI is headed, and what does that imply for this target in Rust because the component model is based on a sort of new approach to interoperability between smaller WASM modules, if I'm not mistaken.
Right. This is sort of how I was saying earlier about wasm-bindgen, how WebAssembly talks in integers but you really want to talk in strings. And so wasm-bindgen was this method of, let me assume a large amount of JavaScript glue, or not say large, just an appropriate amount, and that'll do all the translation between you. But this really only works for the web because out-of-browser use cases, for example, don't have JavaScript interpreters. They don't have this entire platform to build on. So the idea was that to have WebAssembly be successful outside of the browser, and to also have it just be a lot easier to use in the browser, we need a way to talk about more high-level things where all of this can sort of be implied by the WebAssembly binary itself. So today, if you generate a binary, it's a core WASM binary. We have no idea. Is that I32 a pointer? Is it a length? Is it a file descriptor? Is it just a random integer? You don't actually know. But the idea with the component model is it gives it it's a layer on top of core WebAssembly, which is a much more structured type grammar. So it actually has strings, it has records, it has lists, it has variants, enums, all the fancy things you would expect from Rust. And so the component model allows you to bake all that into the binary itself. So the binary is self-describing of, I have a function and it's going to give you a string, and you got to give me a function where it returns a string, kind of stuff like that. So this is where it's much more suitable for out-of-browser use cases, because as an embedder, we can take an arbitrary binary and actually run it. We don't have to guess what's this integer, what's this I32. It gives you a much richer sense of kind of communication on both sides. So, and WASI, for example, is intended to move in this direction, where WASI will be defined in terms of the type grammar offered by the component model itself. So this is what I work on my day-to-day job at this point. So I'm very heavily involved in all of this, but that's where that's a lot of the effort that's been going to WebAssembly, for at least that I've been doing for the past couple of years.
That's awesome. Thank you so much, Alex, for that insight. Well, I want to be conscious of your time, and I want to be very thankful for. I am thankful for the time you're lending us. I also want to give folks an opportunity to get some of those questions to you. So, my last question would be, both of these targets were originally written in 2017 and 2019, respectively. I'm wondering how have things changed since then for both these targets? I know there was a rename involved, perhaps.
Oh, right. Yes. Sorry, you have these leading questions, and I keep forgetting to get to them because I'm too busy talking about other things. But yes.
No,
so the
point.
the unknown target is actually pretty stable. It hasn't really changed a whole lot since it was introduced. Now we got wasm-LD, which was the linker, but after that, it hasn't really seen a whole lot of changes. The only major thing was we added SIMD, so it's sort of an extension to the WebAssembly proposal, but it's just some extra APIs and standard library you can call if you want. You don't have to. But the WASI target, the more major change there, it was renamed from WASM32 unknown WASI to WASM32 WASI. Now we still call it a target triple, despite there only being two things. Don't ask me why, but this was modeled after, I believe, Clang and C kind of settled on the naming WASM32 WASI, and so we changed the name. We changed the Rust data to make sure these two are kept in sync, because we want to keep the Rust and the C target in sync as much as we can. But other than that, that's also pretty similar in terms of not a whole lot has changed since then, where it's been pretty stable. It's been not a whole lot of WASI itself has not undergone a very large amount of change in the meantime in that regard. But yeah, it's been chugging along since then. It's been used by a lot of folks in a lot of different scenarios, and it works pretty well.
Awesome, thank you. Well, that answers all of my questions. I've got a closing, if I may, but I do have two questions here from the chat. And folks, if you've got more questions, keep them coming in, like time allowing. Alex, please give me a sign when it's time to go. So I'm going to bring up this question from Steve, who's asking, on the topic of LLVM, was there ever consideration to use MLIR, or did Rust's WASM backend predate it? Or was there enough Rust C plus LLVM main project integrations that made more sense to not use MLIR? So thank you for your question, Steve. I'm going to tack on one tiny bit to that question, if I may. What is MLIR?
Unfortunately, I also don't know. So
Oh no!
I'm aware myself. I am relatively certain that the WASM backends in LLVM probably predated MLIR. I'm just gonna say MLIR because that's kind of what I say in my head whenever I see it. But
Fair.
I remember I've seen stuff on the LLVM mailing lists and like the weekly updates and things where I saw Enlear a lot more after like 2017. So I think it didn't exist. But that being said, I don't know enough about it, and it might actually make a lot of sense to use it. I think what I can say though is for the current LLVM targets or the current Rust integration, I think one of the reasons we've settled on this is it's very, very similar to all the other targets. So the integration for WebAssembly looks very, very similar to the integration for ARM and x86 and PowerPC and all that business. So I think in that sense, that's one of the main reasons we switched to the LLVM backend was it looks so similar to all the other targets. Now, but again, I'm not entirely certain how Enlear would change this picture or perhaps make it different.
Cool. No, thank you so much. Steve, if you're still there and you want to like give us a link to what Emler is, and yeah, that'd be super cool. Thank you. So I got another question from Kushal, who's asking, when can we use bindgen to use wasm, say written in Rust, inside of Python again? And I'm interested in that again part.
This is where my work on the component model and kind of the work that my colleagues have been working on has been going on for a very, very long time. We've had at various stages, we've had various demos for various things. And so I know at one point, it was where you could have kind of talking with rich types in Python and kind of all worked. And I think it did actually work with wasm-bindgen, the project at the time. Now, in any case, we've long since departed from that. But ironically, this is actually exactly what I'm working on like this week. So there's a project called WebAssembly, which is in the Bytecode Alliance organization, which is tasked with, given a component, I will generate Python bindings to run that component. So this is working at a different layer. This isn't using wasm-bindgen. It's not using literal wasm-bindgen. It's also not using core wasm modules. I mean, it is under the hood. But the idea is it's given a actual component, which is sort of the new thing, we'll then generate all the Python stuff for that. So the idea is that very soon you'll be able to pip install Wasmtime, and then you can run a command there to get some generated Python, and that's all you need. Given a component, you can start running that, and you can communicate with the Wasm with strings and all that good business. So in terms of when, this is all sort of tied up in the component model, where the component model is always sort of just around the corner, but the idea is we're all working very heavily towards it, and it's all it's definitely my personal primary focus and many other folks as well. So I'm not going to commit to any particular timeline here, but I can definitely say that is literally what I'm working on at this moment.
That's super cool. Great. Thank you so much for the question. That's all the questions we have here live. I'd like to close this off by asking you two more questions, if I may, Alex. First off, are there any other projects in or outside the space that you're working on that you would like to show off for us?
Definitely. So wasm-bindgen that I just talked about is probably one of the primary ones, which is kind of wasm-bindgen and the component model are kind of the two big highlights. So the component model is sort of the next generation of WebAssembly and communicating with an embedder and having a much richer language to talk with. And it's not only that level of communication, but it's also WebAssembly modules communicating to each other. Where today you can't really have two different WebAssembly binaries that talk together and kind of work really well. It's all possible, but it's very clunky and it's not really standardized and it's very difficult to get that working together. But the idea with the component model is sort of make even that aspect working, where one program you could sort of bundle everything together, have lots of little modules inside of it. They're all communicating via different address spaces and strings. And it's all structured and everything. So anyway, that's like there's a lot of exciting stuff going on there. A lot of work happening in wasm-bindgen that's actually getting this all working in guest languages and host languages. And then, of course, I can also plug Wasmtime, which is the WebAssembly runtime that I personally work on. But yeah, those are sort of like the main projects. And I mean, I also plug Rust. Rust is a great project to get to dive into. You mentioned that it was you've never actually contributed, but you were sort of reading the PRs. It's super easy to contribute to Rust. That was always one of the best aspects of the Rust project was you can just show up, have a couple of PRs, and get merged in no time. And it's actually really nice because to get called out in like release notes or kind of look at the contributors page and you see your name in for that release or anything.
Thank you. I'm just dropping a bunch of links here.
Thank you.
No. You're good. You're good. No, this is why we do it. Okay, we got one more question. You got time for one more, Alex?
Definitely.
Can you talk more about the component model? Also, can higher level ABI and components be also used for a higher level native ABI compared to only the C ABI?
This is an excellent question. So the component model is, oh dear, how much more to talk about that? I'm talking about the other thing first because it's actually easier. So you're not the first person to ask of what about component model for just native linking? Like I want to dynamically open a library and I want it to not be super raw, super unsafe, and everything terrible all the time. And the answer is perhaps. We've explicitly said we're not going to work too much on this yet. I do think there's a lot of possibilities in it. We're sort of like I can sort of like the way I think about the component model is I draw parallels to sort of existing things to kind of wrap my head around it. Anyway, how to explain it? So I think of a component as a process, like a Unix process. So it's got its own address space. It's all isolated in there. If that thing crashes, it kind of keeps just that, like that. It crashes in there, but it doesn't affect the rest of the system. So if two different components are talking to each other, and one of them crashes, the other one's totally fine. But then additionally, when you communicate between two processes, you can't just pass a raw pointer because you don't have access to my address space. So talking is more like an RPC kind of thing, where we're going to use the component model as sort of like there's some IDLs going on. Not quite. None of this is a perfect analogy, but it's like kind of roughly there. So I would think of like in that analogy, I like this very clearly goes to Unix processes, dynamic loading, and all that good stuff. And so I do think there is a possibility to work towards a native solution there, but we got to get the actual component model working first. So we're going to do the WebAssembly part first, and then maybe go and revisit it afterwards. But anyway, along the component model, that's sort of how I think about it. Is like different processes talking over a strictly typed web IDL. They can import and export things from each other. This is like kind of you get all the features of WebAssembly, and then internally you can also be architected however you want. If you want to be built of 4 core WebAssembly modules linked together in some weird fashion, great. Component model allows you to do that. If you want just one core WebAssembly module, that also works just fine. But one of the key features of the component model is I've been talking about processes and IPC, and typically whenever anyone thinks that, they're like, oh, that's probably slow or not really suited. But components are intended to be much more lightweight. So similar to how you can instantiate a WebAssembly module, an entire WebAssembly module in microseconds, that same sort of thing applies to components where you can't really start an entire process in a couple microseconds and be, or I don't know. I'm not going to claim that because I haven't actually run benchmarks on Linux or anything like that. But the idea is that components are very lightweight, very easy to communicate between these small tasks. And so where you might previously have like a bunch of different servers talking to each other, you could sort of slurp all that together into one component and have them talking very quickly to one another, have a nice sense of locality there. So that's like the component model whirlwind. I don't know. The component model is a massive topic. I could talk for hours about that. So happy to answer specific questions. That's like, I guess, the highlight, very 10,000 foot overview that I can give though.
Cool. Thank you so much. Alex, we just had one more question come in. I'm wondering.
Totally fine. Happy to keep going.
Awesome. We got a question from Mosaka on Discord who's asking, how will WASM threading proposal affect the Rust WASM 32 WASI target when it lands?
An excellent question. And I think the answer is I can't commit to anything. So I'm not the one leading these proposals or leading these designs. But what I can say is that the current thinking is that there's going to be a WASM32 WASI threads target, something along those lines. Might not be called precisely that, but it's pretty unlikely that the default WASI target is going to grow threads. And this has to do with threads in WebAssembly are kind of funky. They're just real different of how everything else works. And sort of on a native platform, you just assume threads are always there. Like you just get, if you download x86-64 unknown Linux GNU, it'll run just fine. You can spawn a thread, you can not spawn a thread, everything's the same. But WebAssembly is different enough, especially with threads being not a, I guess they're shipped in browsers, but the proposal and the proposal process is not fully along. So anyway, there's a lot of stuff in the air around threads, and that's why it's probably going to start out as a threads target. And perhaps in the distant future, these are going to merge together back to just one WASM32 WASI target. But given the status of threads in WebAssembly, which has its own set of big open questions, we're probably going to have 2 separate targets from now.
Cool, thank you. And I got to thank you for the answer. Will components also help get closer to native WASM bindings to the DOM and the other web APIs without needing to go through JavaScript?
This is the irony is here. The irony here is that so I started working on a lot of this with wasm-bindgen. So at the time, the current component model proposal was called WebIDL bindings, And I was like, okay, that was the whole point, was let's have a WebAssembly WebAssembly module. When it calls the DOM API, it goes directly to C++. So it doesn't go through JavaScript, doesn't go through WebADL bindings. It just goes straight to C++, like in the browser engine itself. That was the theory. So that actually evolved later to something called interface types, and then that evolved to the component model. So very storied history here, but the idea is, yes, more or less, it's going to take browsers a very long time to get to the point where we can actually go straight to C++. So for the developer point of view, the component model is very much geared towards you in theory wouldn't have to touch JavaScript that much. Like your component is self-describing enough of I'm giving you a string, you're giving me a string, and then given some suitable configuration, you could kind of imagine like if I import from the global, it like gives me a bunch of global JavaScript functions. There's a lot of JavaScript quirks to get through, but like the developer experience is effectively wasm-bindgen right now, which is you can write your Rust code, it'll auto-generate most of your JavaScript code. We don't have to worry too much about that, but the runtime aspect is still going to be going through JavaScript for the foreseeable future. Now, 10 years from now, if the component model is super successful and is very widely deployed and very heavily used, I could definitely, like, it is very much a feature we want to have, which is that when you put a component in a browser, it'll have native component model support, and when you pass it in a DOM function, it'll just hook it up directly. So when your WASM, which is compiled code, calls DOM, it goes straight to C++. No validation, nothing in the middle. Now, there's a lot of caveats on that, very far future, but that is the hope eventually.
That makes me think, I mean, most WASM people who do WASM who know that cartoon illustrated guide from Lynn Clark. And I think of that drawing where the WebAssembly is sort of like reaching around and to going into JavaScript from the other side. Do you know what I mean?
It's true, yeah. It's JavaScript has its own setup. This is actually very similar with threads as well, where eventually the goal is that right now you can only spawn threads with web workers, but eventually what if you had a thread spawn instruction in WebAssembly? WebAssembly itself is much more lightweight, could get a much more lightweight thread, so kind of a lot of issues, or so I've heard, around web workers can in theory be solved by this, because that thread model would be much, much cheaper, is the theory. But this is where WASM very much wants to reach around JavaScript and be like, I don't really want to touch you. I want to go straight to C++. So we'll go kind of get the nice fast path through there. So very much intended to happen eventually.
Cool. Well, I think we can wrap up the live portion here with one final question, which is from Kushal and myself. Where can we find you for future live questions? Where can we get in touch if we want to follow your work?
Definitely. I'm mostly active on GitHub, so my handle is my name, Alex Crichton, just all one word. Feel free to I'm very active on Wasmtime nowadays, but a lot of other repos I've been attached to historically. Otherwise, I don't actually do a ton of social media stuff, so I don't have a Twitter. I do have a Twitter, I just never look at it. But feel free to email me. I'm kind of a little old school in that regard, but yeah, happy to take emails, happy to take questions on there, or reach out to me on Zulip as well. So I'm on the Rustling Zulip at Alex Crichton, and then also the Bytecode Alliance has its own Zulip for Wasmtime as well, and you can also reach me there.
Wonderful. Thank you so much, Alex. This was highly interesting and enlightening. Really appreciate it.
Fun for me, and thank you so much for having me.
Thank you very much for both of you, Ramon for preparing the interview, and Alex for taking the time to answer all the questions. We're going to tie it up with a bow here, and I invite everybody to follow the Discord link that's in the ticker and also in the chat to come and hang out afterwards if you like. And otherwise, we're going to end the live stream now. Head over there, and I hope everybody has a great morning, afternoon, evening, or night, depending on where you are. We'll be back with another one of these in January. So please do send us a message, either email team@suborbital.dev, Twitter. I'm Cohix if Twitter is around for too much longer, or just find us on Discord or wherever. If you have a demo or if you have somebody you'd like to see interviewed or whatever, just let us know. So thanks, everybody. And that's it.